Good morning. We're getting started here. We're going to spend most of the day in Chapter 3 learning about the Z-transform, which is probably one of the most fun topics. It seems perceptibly easy, especially from your past experiences, but this book takes you on a different, more in-depth tour of it, in that we're going to be looking at the two-sided Z-transform very intently. And we're going to be working with regions of convergence then, since those are the things that control whether the sequence is right-sided or left-sided. And we'll get into what I mean by right-sided and left-sided and how all of that works. It's actually still a lot of fun, though, and inverse Z-transforms is the dominant activity in the homework, and using partial fraction expansion is the primary technique that we'll use, which you've used before. And then we have tools in Python there that can help do that numerically as well. Before we actually go there, though, what I want to do is finish up one example from the end of the last chapter. I jumped ahead just at the close of class to cover things for homework that was due, but I skipped over this example called windowed sinusoid spectrum. And this is a really important topic. It's a topic that really transcends just plain old hardcore DSP math, but goes out into the test and measurement world big time. I mean, you use an oscilloscope that has an FFT spectrum analyzer built into it. You use an analog spectrum analyzer, and they both relate to this concept right here. And these are all the mathematical details in a simplified form, but then I'm going to jump over to the Jupyter Notebook so we can just explore some of the things. So we were talking about an ideal low-pass filter, and this is connected to the ideal low-pass filter when I talked about windows, and that's what this guy is right here. Get the right pan out. That W sub n is the window, and in this case, it's starting off being just a mundane rectangular window. Basically, it's just something that gates the signal on and off. So you can think about it if it was a data acquisition system and you were streaming some data at yourself from a sensor. In this case, it's a very simple sinusoidal signal, but it could be, all kinds of different waveforms. But you're going to gate it on and gate it off, or you're just going to capture a buffer. Maybe you've played with, have any of you played with software-defined radios, where you build a capture, like if you do it in Python or any language for that matter. New Radio Companion also lets you do this too. You just capture so many seconds or milliseconds or whatever. So you have a record of data, and now we're going to do something with it. So this picture down below there just depicts that idea that the signal is flying at us, originally a continuous time sinusoid in principle, and then we're just taking a picture of it, a snapshot of it, and if it's discretized, then it's the stems, and then if it's a capture record, it's the stems that are filled in. So we're taking, in this case, m is equal to 10, and the amplitude of the sinusoid is 1, and in this example, it's omega naught is 3 pi over 4. And if you want to convert that to normalized digital frequency, you divide by 2 pi, right? So you could get that. I guess this is, not that it's a super big deal. There's a slash in there. Yeah.
Would I know those if you didn't give those? Like, could I assess that diagram that you've given and
of course.
Out A equals 1, yeah, that's my question. Could I have figured those variables out?
You mean the parameters?
Yeah, parameters. Could I have figured that out without you giving them? Just
No.
Looking at that?
Just by looking at the picture, no, and that's kind of what the whole thing is. If we're doing data acquisition, we're capturing, we're trying to estimate something, and that's one of the other courses I taught all the time was statistical signal processing, which is closely related to machine learning in the data science world and things of that sort. But estimation theory is something that would take information and then you would estimate parameters related to some model that you're saying, this is what I think I have out there, but I don't know what the parameters are. And the parameters could be magnitude or amplitude A, frequency, omega naught, and a third variable would be the phase of the sinusoid, perhaps, depending upon the type of capture you're doing. So that's a good question, and that's what we're going to see, how well in the frequency domain we can assess what's really out there from this capture. And making M really small, 10 samples is, what do you think? Is it a lot of data or is it minimal data? It's minimal, but you know, it's what you're going to get to see is how well and how much you can actually do with very little data. And data acquisition means time is consumed to capture it, and if you have to make a decision quickly, you don't want to spend a lot of time capturing data. I'm thinking right now what's maybe going on in the Middle East with missiles going back and forth and electronic systems defending. I'm thinking of Israel, you know, what do they call it? David something or another. Whatever they call that.
Iron Dome.
Yeah, the Iron Dome. That's basically some system that's estimating the arrival of some objects traveling through space and trying to intercept and destroy them before they get too far down, I think.
That's insane. 200 missiles. And that's what I was explaining to my 14-year-old. He was asking what we were talking about in class. I was like, well, something has to decide whether or not that's an airplane or a missile.
Yeah, and that just blows us up. This is a simple example. Let's not get too carried away. No, we're good though. You're thinking correctly, right? That's what you learn in school is fundamentals, and then you get exposed to the bigger picture later. So the cool thing about this example is it's going to use the windowing theorem from Fourier transform. So first off, we can take the Fourier transform of the cosine, and it's going to be the delta functions that we've seen before. So that's table entry number 11. And then the Fourier transform of the window, or I guess what I really need to explain here is that if I change the colors, yeah, we're having the lag problem that we did last time for whatever reason. We have the product of two signals in there. We have a cosine, and then we have Wn. So this is multiplication in the time domain, and what should be burned in your brain from linear systems theory way back is the dual property, right? Multiplication in one domain is convolution in the other domain, and that holds in the discrete time domain as well. So we're seeing multiplication in time will be convolution-like, but because we have periodic spectra in the discrete time domain, it's a what we'll later call a circular convolution or periodic convolution. So that's what we're headed for right now. We're saying we're going to get the Fourier transform of each of those two components, and then we're going to do some convolution-like operation, but it's actually the windowing theorem. So the rectangle is from table entry number 9, a sine mx over sine x. This was what I called the alias sinc function. That's in the frequency domain for the rectangular window. And now we use the windowing theorem, which was written out a few pages back. It's a fairly messy looking theorem, but this is an opportunity to try to use it. This is the theorem right here. We have x times w, and now we're going to go through this integral to get the transform domain result. And this is like convolution in the frequency domain, except it's periodic. So in the definition here, you see that you're integrating from over one period. It could be minus pi to plus pi, 0 to 2 pi, whatever 2 pi interval you want. So I'm writing that out down here. And the fact that we have delta functions inside of here means that we have some nice things happening. So the way I have this written out is we have the integral outside, and then one waveform is inside of here. And that's the waveform that has theta minus omega naught on it, omega naught in it, and then, or theta minus omega naught, and then in the other waveform, we have the sinc function with omega minus theta. Got things mixed up a little bit here. Theta is just the independent variable of integration. So we have capital X of theta up in the blue, and then we have omega minus theta in the bottom. And when we integrate out through theta, we'll end up with something that's a function of omega, and it'll be our X of e to the j omega spectrum. And because there's delta functions in here, and the fact that on this interval from minus pi to plus pi, the two delta functions you see inside the blue circle, it's grotesquely overblown. I mean, there's delta functions represented by that across the entire axis. We really only need to seek out the delta functions from that sum that are going to land in the interval minus to plus pi. So that makes things simplified in the next line down tremendously. It's basically sifting out the delta functions are hitting the sinc function in red at just two locations, one positive frequency and one negative frequency. And that's what you see here. We have that, we have that. So those are the two blobs, the spectral blobs that get created at plus and minus omega naught. And when I say spectral blobs, it's because this sinc function is getting reproduced at the location of the sinusoidal frequencies, which would be plus omega naught and minus omega naught. So looking at it, I'm going to go real time on this in a moment in Jupyter, but just looking at the code right here. So I set up the example of saying, let's let m is equal to 10, let's set omega naught equal to 3 pi over 4, create an index. We only need to create an index over the range of 10 points, 0 to 9 is what this would do in Python. Then create our sequence. This is the captured portion. And then the rectangle is created, but in reality, as it stands right now, this rectangle is not really performing any exotic function because we're already creating the cosine just at those points 0 through 9. So the rectangle doesn't mean anything, but it's setting the stage for what I'll do in the notebook, and that is where I'll change the shape of the windowing function. Rather than letting it just be a boxcar, as it's called here, chops here and here, flat across the top, I'm going to replace it with a window that has a taper to it, or a shape to it. We'll see how that impacts the spectrum estimate. But just carrying it out like this, I'm going to use then this line right here is pretty important. And this is something I didn't get a chance to talk about last time either. But it tells you that you can use freq z as a means of estimating the Fourier transform of a sequence. The Fourier transform of a sequence, if it's infinite in duration, requires the sum from minus to plus infinity. But if it's finite in duration, you would just have a finite number of terms. In particular, if the signal you want a Fourier transform lies on the interval 0 to, say, m minus 1, which is what we have here, then you can just put that entire waveform in the numerator coefficient array for freq z, which is b, the b vector, so it's the first argument in here. So it's right here. And then this is just set equal to 1. So this is a repurposing of the freq z function that was defined earlier, just putting the signal you want a Fourier transform in place of b, which is the numerator values in the ratio of polynomials in powers of e to the minus j omega that we saw last time, and you used freq z also in the homework, right? It's not exactly a magic box. It's something that both more fully understand, but really what it's doing is it's taking the FFT on the first set of coefficients and then on the second, and then it's dividing point by point. That I can talk more about later, but right now you can just think of it as a box that will take the Fourier transform at discrete frequencies, and those discrete frequencies are defined here. I guess I didn't define F in here. It's the same F that I was using earlier, though. It's an index array that goes from, F was going from 0 to 1/2 with a certain resolution. We'll see that in the notebook here in a second. So then I can display this, and what I did here to display it, this is blocking it, so I displayed it by taking the absolute value, but then I normalized by the number of points I have in the capture, which in this case is just sum of the rectangular window. That just normalizes the amplitude. So it's going to come out to 1/2 in this case for the sinusoid. And then I frequency axis label and so on. So this is what the magnitude plot looks like for m is equal to 10, and it's not in dB yet, but it will be shortly. This and this are in place of the, if this was a theoretical, I'm not drawing a straight line very well with this piece, but the ideal spectrum would be something like that. It would be a +1/2 and a -1/2 at plus and minus omega naught, which is, that is omega naught over 2 pi. Normalized frequency. So you'd look at that, and what I want you to first notice is that it looks actually pretty good. If you were trying to estimate the frequency, you could use some peak finding function, which is available in NumPy. Find peaks is the name of the function, and you'd be able to find where that peak is. If you're worrying about getting cheated on using find peaks, you will have it in the first project, so you will be getting to use that function later. But you'd be able to find out that frequency pretty accurately, because right now there's no other signals in there to clutter things up. Agreed that that would work? With only 10 points, it's actually pretty amazing. Now, if you want it to look more like a delta function, we'd have to increase m, and I'll do that here in a moment. But 10 is pretty tiny. One of the things you're supposed to notice though immediately is that these are the side lobes, and this is the peak. And when we go into dB levels, those side lobes are pretty high. And if there was another signal here that was close to the frequency of the signal that we put in, the bigger signal, it would produce a superposition. It would superimpose another one of these blobby things, but it would be hidden down over in here, and it would be washed over by the side lobes from the stronger signal, and that's called leakage. The primary signal is leaking energy out in the frequency domain to the other bands, and then it can mask over a weak signal, like it might, putting it into sort of military operations terms, or even the vehicles on the highway with a radar system tracking, is there a car in front or behind? If it's a small object, maybe it's a motorcycle, it will have a less radar cross-section, it would have less return, and it might get lost in that clutter or that leakage. Too bad. I mean, I'm just saying that we can only do so much with so much data, but you got a question? Somebody had a question.
So does the M correlate to the amount of peaks that we're measuring here?
Yeah.
Or is that just a coincidence?
No, it does, because if you go back to the sync function up here, this guy right here, that's how many peaks there's going to be, starting at 0 and going up to 1 minus to the frequency. Well, let's do it like this. I think I had a picture of this. I'll try the pen again and see if I can get it to work. It repeats again at 2 pi, so the number of peaks here, counting starting at 1 at 0, 2, 3, 4, 5, and so on. That's going to be less, if you don't count the 1 where it starts to repeat, that is going to be 10.
That's the +1.
Yeah, that's the 10 that are in there. Now these peaks of the window itself occur starting at 0, and then we're going to look at that actually more today too, in the Z domain. They occur at multiples of 2 pi over m. So we have something like this. Up to n minus 1. What happens though when we're doing this convolution is that whole spectrum shape there, the window, gets shifted up to omega naught, and then is shifted down to minus omega naught, and then all the other terms that show up in the convolution are superimposed, but that's taken care of by the fact that we have this alias sinc function already, so they're shifted, is what I'm getting at, though, is that these shapes here are not the original ones, but they've been shifted by the signal.
Now I see the 0 in the middle now.
Yeah. So that's all there is to that example, but I'm going to go over to, actually do this first. Go over to the web browser. And I have this up here because I was going to say something about a reposting, but at any rate, I will slide down into here, and we're down here into this spectral estimation and windowing area. So here's the same problem setup, and I can repeat this problem by just saying, okay, I've changed this around a bit, so I'll just go with the same values that we just had. Only thing I'm doing different now is I'm actually bringing in another window function. And remember last time I told you that that's right. My system had to restart last night, as Windows frequently does, so I think this has to be started again. I'll make sure it's clean, restart the kernel, and I'll go back down here to this section. Okay, so now it ran, and if I go down here, this should be good to go too. So these are all the window functions that are available in scipy.signal under the .windows directory, so to speak. So I'm going to be introducing, let's see, I did that right. I'm going with a Hanning window or Han window. And if I type a parenthesis there, I can go Shift-Tab, and I can get the definition of the Han or Hanning window. Remember, we talked about that last time. The guy's name is Han, and then it was slang interpreted to Hanning's window. Like, I went to school in Upper Michigan. Most of my colleagues in school were from Detroit area, and what do they make in the Detroit area? Cars. So people would say, I work at Ford's. They didn't say GM's, but Ford's was always an apostrophe S at the end. It was really bizarre language. I work for Ford's. That's just where you grow up, right? If you grew up in the South or different parts of the country, people say things that are kind of awkward sounding, but at any rate, Han is the window, and we're just going to set the length of it. So here I create two windows, one rect and one Han, and then I'm going to actually do the multiplication right here. And I think I already ran the cell, but I'll just run it again. And then I'm going to go ahead here and plot it. Plot in the time domain what I'm seeing, and I didn't use a stem function plot because when I try to overlay the stem, it just looks, it's very hard to figure out what's going on. So I'm just connecting the dots, but just the idea is you're seeing with the rectangular window, the samples of the sinusoid are in the blue, and that's regular looking, and then the thing that's shaping down is the effect of the hand window. So now I'm going to go ahead and do F from minus 0.5 to 0.5 with a very high resolution, 0.001, and then I'm going to plot things in decibels by doing 20 log base 10, the absolute value normalized again, and then plot that up. And okay, I thought I plotted it. There we go. So we're seeing, like we saw in the notes, in the blue one, we're seeing this, these side lobe levels are very high. With the handing window, we see how we can drop them down tremendously. This amount of dB between the peak and the first side lobes in the decibel scale is about 13 dB. I think that's what I said before when we were talking about windowed FIR filter design, which is similar to this idea. This is spectral analysis using windows. Design of ideal low-pass filters can be done using windows as well. But the handing window has side lobes that are much further down, and this topic gets delved into a lot more in like chapter 8 or something of the notes. It's way up here.
You're analyzing the same exact signal.
Just changing the window.
And is that more like a topographical exaggeration kind of thing, or?
What, the peaks you mean, or the side lobes?
They're at two different levels, or maybe they're not at two different levels, just one's being portrayed in decibels and one's not. Is that right? Is the hand being expressed in decibels as well?
Yeah. We go up way into chapter 7 of the notes, and I go into this idea of windows, and some of these same things are in here. So this is when we would next see this, but there's a table in here that just describes the properties of the windows. Basic properties of the windows. There it is. So the rectangular window has a side lobe level that's only down 13 dB, whereas the hand, I didn't correct my grammar here, is down 32 dB. And then the properties of these windows that's also really important is the rectangle window only has its side lobes drop off at 6 dB per octave, whereas the hand window drops off at 3 times that, 18 dB. So it's very powerful for clearing the clutter that it would produce, or the leakage. Question?
On that last picture you showed, it shows that the handing window function, its peak encapsulated the side lobes of the
Yeah.
Is that another property of the handing that it's
got a wider main lobe?
Yeah.
Yep, exactly. Yeah, good observation. That was exactly full width in bins. If we were doing it in terms of the FFT, the handing window or hand window takes up twice the width. It's a trade-off. It's like pushed down, spread out more. Question?
Yeah, just kind of along the path that he was questioning.
Should I jump back to the notebook now? Because I'm going to show you more stuff in the notebook.
Generally, to answer his question and make sure I understand it correctly, these windowing functions are mathematical functions which are used to characterize the signal that we're looking at, and define the center frequency or the
Yeah, estimate parameters of the signals of interest.
Yeah, and each different type of windowing function
Correct. That's a good statement.
That's what we're looking at.
Yeah, the window provides a means of seeing things. In the point of the fatter window means you can't resolve a signal as well, and that, Chapter 7 in the notes goes through that trade-off. I hope we can get to that point. I'm usually skating fast at the end of the semester, but it's up there. You can go look at it right now if you want to. This is the beginnings of it, though, and I wanted to just, I don't know, I think it's fun to see some applications of where you can go. Spectral analysis has been really big in my life over the years. It factored into my dissertation, and it always shows up in a comm system implementation. It showed up in discussions at our stand-up meeting yesterday about how am I going to test this on this project, and they were talking about spectrum analyzer and spectrum analyzers and things, and I was making my comments too. But so this is good. Another terminology thing that maybe doesn't matter a whole lot, but in the type of work I was doing at the previous company and I've done at other places, the acronyms are SOI and SNOI. SOI is signal of interest, and SNOI is signal not of interest. So that's kind of a military kind of an intelligence gathering term. What are we interested? What are we not interested in? And then people talk about how to classify this, and they pronounce the acronym too as SNOI and SOI. So SOIs and SNOIs. I'd learned that a long time ago. It's kind of crude sounding, but engineers have to pronounce their acronyms, right? It's nice, though, to work that way. So let's just do a variation on this. Let's go up here and just see how things would get much better if I made this 500, 10 times as many samples. So now we'll go down in here, and we have a lot more cycles. The window shape is far more discernible, of course, too. But now we do this, and now you'd say, oh, it's looking pretty good. I mean, both of them are looking pretty good, but you can still see, now you can understand why that 6 dB per octave roll-off rate is still a problem here. In decibels, it's still, you know, it's there. It's not any better. It's still only 13 dB down for the first side lobe. And the roll-off rate is being slower, whereas here it looks nicer, and we can overcome the fatter hand window by having more points, because as the points go up, the width of that window goes down, because it's proportional to 1 over m, so it gets smaller. So that looks pretty good. So now, what's the next thing I could do that I did here, and I don't want to spend a whole lot more time on this. You can play with this in the notebook, though, and keep this moving around so much. What I want to do is, wait a minute, I jumped to a different example. Yeah, there's too many examples in the notebook here because every time I've taught, I've added something more and then I keep uploading it. So you got to cut through the clutter. What I tried to do, there's all kinds of features, and I'm going to be demoing to the customer tomorrow using a Jupyter Notebook. You can turn things off. You can take a whole section if it's got the same heading. You can go in here and you can, you know, you can close things down. You can, it's kind of nice. I've lectured a lot off of the Jupyter Notebook, not just in class, but I mean in presentations at meetings. So I had it turned off and I accidentally touched the screen and opened the window back up again. So what I wanted to do here was go back to another variation on this, which was that, and then I'm going to bring a second sinusoid in. So now I'm going to have omega naught is going to be smaller. It's going to be at 2 pi over 10, and then I'm going to have another one at 1.5 times 2 pi over 10. And I'm going to take that back to 50 just for a second here. Look in the time domain, and you can't tell, I didn't point out here, but the one signal is 1/10 the amplitude of the other, so you really can't make anything in the time domain about that weak signal. And if we go here to the frequency domain, can you tell that there's another sinusoid in there that's 1.5 frequency? This little, it's trying to push its head up, but it's getting clouded by the backwash from the leakage from the dominant signal in here. But if I brought it in closer, it would actually, this little blob here would fall underneath that big peak, and it would be totally under its shield and not be seen. So the solution here, though, is just to say we're going to have more samples. So if we, again, take this up to 500, you still won't see it in the time domain. At least it's hard to perceive in the time domain. It's now very discernible in the frequency domain, even though it's down by a factor of 10. And what is a factor of 10? If it's an amplitude of 10, and that's like a voltage gain in uses of decibels, so how many dB down should it be in the spectral domain? If I take the amplitude, drop it by 10, that becomes 20 log base 10, right? So it should be down 20 dB, and that's, here we're at about -5, and here we're at about -25. Is that making sense? Okay. Those of you that might have taken the COM lab, did anybody here have it? You use the spectrum analyzer and you have learned how amazing it is, right? It's your spectral domain eyes which see things you can't see otherwise in the time domain. Any other questions? I mean, there's a section in here on windowed FIR. I'm not going to take the time to do it, but it talks about how you can use this windowing to design a practical filter that has really good side lobe rejection and makes a good low-pass filter. And you'll get a chance to play with some of those things later. So, good to go. Back to the notes. So now we're going to leave that, and we're going to go to the Z domain, and it was down the page there because I was studying it during my breakfast. Okay, this chapter is, this is the table of contents, but we're going to go down into this inverse Z transform as far as we can get today, and then we'll probably do some more wrap-up. Right now the homework set number 3 is due nominally a week from today, but I'm probably just going to delay it again till Friday because I think that's probably a good pattern. Has that been okay for most of you? Okay, okay. It's helpful to me too because I have some, I'm covering my butt basically by having a little bit of padding there. And I'm a person that doesn't have the padding. What's that? Yeah. I wake up on Saturday morning and hope to be surprised. I was a little bit disappointed on Saturday, but, you know, everybody's here. It's just I didn't see all the papers I was expecting to see. Okay, so what, and I guess another thing that's in this chapter is a remnant, but it's no longer really in the book, is all of this stuff using contour integration and complex variable theory. I've left it in the notes because I spent a long time giving some background when I wrote this chapter initially many years ago, and I just can't give it away. I don't want to take it out of here. I will be pitching at times, though, as I go through here in the beginning, that the Z transform uses a lot of neat properties that come from complex variable theory. And electrical engineers, we think we know complex variables, right? I think we know complex arithmetic really well. Complex variable theory is kind of goes beyond just the arithmetic part of it. So when I was getting my master's degree, I took a math course called Complex Variable Theory, which I thought was good. It opened my horizons. So if you get a chance to do that, you might want to think about it. It's helpful in electromagnetics work too. I took boundary value problem solving, which is definitely related to partial differential equation solving, and that factors into electromagnetics, electro-optics, and other things. So don't be afraid to take math courses, but you have to be brave, and you have to be durable, and you have to not be intimidated. But as a graduate student, they were good. I took a lot of extra classes just because they were there, and I went to a small school, didn't have a lot of courses that were offered as electives, and I just took my electives mostly from math, sometimes from physics. That's where I took my advanced electromagnetics, was from there. So why the Z transform? The big sales pitch is it converges to a broader class of signals than the Fourier transform does. It provides more convenient notation. The Z transform is much cleaner than the Fourier transform. E to the minus j omega is, or e to the j omega is going to be swapped out and replaced with Z. It's still a complex variable, which we could say is on the unit circle, e to the j omega, but by just keeping it in the notation as Z, it seems so beautiful, right? Just like the Laplace transform S covers for j omega along the j omega axes. And lastly, it's the power of complex variable theory, which effectively utilized. As an engineer, we're used to being handed tools that we can use to do our job. And we abstract away at a level below all the details. And that's kind of the way we do it here. And that's the way engineers do things. We're always abstracting details so we can concentrate on a higher level. And abstraction, I think, is about the only way to manage engineering complexity, right? I do not want to build chip resistors, let's say, for my PCBs and learn all the ins and outs of chip resistors. Somebody else is going to do that. Some one of you could be doing that someday, but not everybody has to worry about that detail level. Okay, the transform that the book focuses on is the bilateral, which means it's defined from minus infinity to plus infinity. And the operator notation is script Z, or math cal, as I showed you the other week in LaTeX code you might put in the notebook. Math cal, curly braces, capital Z, will replace that character. Calligraphy Z is a sum over the sequence or impulse response, whichever, and then weighted by Z to the minus n, where Z is a complex variable. And that produces a function, capital X of Z. If it's a transform pair, it's the double-ended arrow with the Z over the top to relate X of n to its Z domain counterpart X of Z. If we wanted to step back to previous course in signals and systems, you might have dealt with the one-sided or unilateral Z transform, and that is perfectly okay, but not the way this book works. It's covered at the end of this chapter, and it's primarily of use for solving initial conditions problems. And I want to just point out right now that it's what you grew up with in the Laplace transform. You looked at differential equations for circuits, remember initial conditions on capacitor voltages, inductor currents, and all that stuff, and you got so sick of looking at I remember integral differential equations, all that yucky stuff on the page, and then you said if we go to the S domain, we can solve much easier, and then we have methods that we can handle the initial conditions with the inverse Laplace transform. Does anybody want to comment? What did you think when you first saw that?
I mean, it was kind of eye-opening because differential equations are real messy and not fun
Right.
to deal with. So then now I can do some complex circuits with just algebra.
Right.
Pretty beautiful.
Okay, that was the word I was looking for. It's a beautiful thing that you can kind of distill that. It's a very narrow class of differential equations, but electrical engineers are pretty content with linear constant coefficient differential equations for linear circuits. I mentioned boundary value problems and partial differential equations. That's where you have wave interactions and interfaces and things. That's also a beautiful thing. That is not quite as simple. It's harder to solve that stuff. But we have numerical solvers available, like with ADS and other electromagnetic solving tools. So we do have that available to us, and I'll talk about that at the very end, but it's not a dominant thing in this class. And the reason why the two-sided Z-transform is so dominant is because it relates to the Fourier transform of a sequence, which ran from minus to plus infinity in the sum, very, very well. And it also deals with the fact that in the discrete time domain, we're abstracted into working on a computer where we might be having signals running backwards or forwards. So we have signals that can start at a point and they can go backwards, or we can start at a point and go forward. So I think the authors of this book, way back in '65, when they were the pioneers of the first discrete time signals book, said this has to be, and even though they revised the book many times, it hasn't gone away. It just stays here, and it's going to get embedded in your brain now too. So how is it connected to the Fourier transform? Just simply put yourself on the unit circle by letting z equaling r, which is a radial component or radius of the complex number, and then e to the j omega is the angle that it takes on. So when we plug that in, we'll have x of r e to the j omega, and then by factoring the r to the minus n out in front, and then having the e to the minus j omega n, it's looking like we're taking the Fourier transform of a new signal, x of n times r to the minus n. And this is supposed to convince you that for any r, you see that you can regularize a sequence x of n so that the Fourier transform can exist. Remember, we had some sequences where the Fourier transform doesn't exist, only in the mean square sense, or Fourier transform in the limit to get delta functions. This r to the minus n is like a weighting factor that will make something shrink and be more easy to sum it in the Fourier transform definition. And we're going to see that when we start doing transforms. But when r is equal to 1, that is exactly the Fourier transform. So this supposedly is hard to visualize in the beginning. When I was first teaching this subject, my mentor, Dr. Ziemer, who was the department chair when I came to the faculty, but he was my dissertation advisor back at Missouri S&T, he said, students won't get that. The Z-transform evaluated around the unit circle is the Fourier transform. But I said, they know this from the S domain and the Laplace domain. If you have the S plane and you go vertically on the j omega axis, that's the Fourier transform. If you sample on there. It works almost all the time, but not all the time. So I'll be talking about that here too. But just to draw the picture of it, and this will be a mental mind's eye view that you want to have all the way through the rest of the class. This point right here is dc, and this point over here is pi in omega, and then you can just pick any other values. I listed some of the other ones off. This is pi over 2, and that's 3 pi over 2 there. But if you're looking at this sheet of paper, you're thinking of this circle as just looking at a top view of the surface formed by x of z, the z transform. And when we just cut around it, and most of you probably don't bake cookies, but I do at Christmas time, and I use a cookie cutter, and you cut something out from the dough, right? So I think of this as being the perimeter of the cookie cutter. Is you take that and lay it flat on a sheet of paper, and that's now the Fourier transform. And then because more and more trips around that circle produce the same thing, that's just the periodic extensions. Remember, the Fourier transform repeats every 2 pi, so start thinking about that. Does anybody not like eating cookies? They can be the death of you if you overeat, right? Yeah. No, it's a reality. I was declared pre-diabetic for a while, and then I modified my diet tremendously, and then I changed doctors, and they weren't so crazy about A1C anymore. The A1C thing is advertised on TV an awful lot, and I don't know. I have a sister who's a family practice doctor, and I talked with her a lot about it too. So I had a doctor, though, that was just fanatical about testing my A1C every 3 months, and it doesn't change. I mean, I'm not saying it's not important, because some of you probably, it means a lot more to your health and well-being to know that. But okay, convergence consideration. So what is the existence of the Z transform? What do we have to have? We know the Fourier transform doesn't converge for all sequences. The Z transform doesn't converge for all sequences, and nor does it converge typically over the entire Z-plane. There's only very specific signals that would converge everywhere, and they're not very interesting at all. So, but we want to know where they exist. So we define the value in the Z-plane where the Z transform converges or is bounded as the so-called region of convergence. And this is an acronym that gets used multiple places in electrical engineering. And when I'm working in detection and estimation theory, I have something called the receiver operating characteristic, which was developed back in World War II for radar and understanding the trade-off between false alarm and detection probabilities. Here, though, it's the region of convergence, which most of you will call the ROC, R-O-C. So if we extend the uniform convergence requirement of the Fourier transform to the Z transform, then that's saying that we have to be absolutely summable over that region of the Z-plane, and that will establish the region of convergence. So absolute summability just says we're going to take the absolute value of the argument of the sum in the definition, and when we factor that through, we see that magnitude of Z just becomes R to the minus n, and then we have the absolute value over the signal as well. So a property of the region, the general property of the region of convergence, it will be some annular region. And there's a whole table in the notes here and in the book about what are the properties of the ROC, because you learn a lot about a sequence from its region of convergence. One of the first properties, though, is if the region of convergence includes a point Z1 in the Z-plane, it will be the entire circle having that radius magnitude of Z1. But in general, like I said, it's an annular region, or annulus is what it's called. I think this is a term from calculus, probably. I don't know. You've heard the term before, right? An annulus. So that's what it looks like. You could view it as a flat donut, I guess, too. If you like donuts, you want to think about that. Or it's a cookie made by cutting it twice. Cut the inside out, cut the outside out, and then you would have something that would be very fragile. That would be that shape. Okay. That's just the generic ROC. So one of the really important things that we're going to be coming back to over and over again, I'm going to be saying, is if the unit circle is contained by within the region of convergence, then we're happy to say that the Fourier transform also converges. So that's going to be a question that will come up in problems, and in analysis you're doing, you'll look to see, does the region of convergence contain the unit circle? And you'll say then it's stable. The system is stable if the region of convergence for that system contains the unit circle. Or if we're looking at the output of a system and we say y of z, if it contains the region of convergence, then we'll know that it's a bounded sequence in the sequence domain, and then we can figure out a lot of other things about it just from the region of convergence. So where do some of these neat properties come from? They come from Laurent series, which is something that I first bumped into when I took complex variables. And I'm not making you learn these things, but I'm just pointing out that a Laurent series is kind of like the definition of the Z transform. It's a sum of something. It's a series. And then the Z transform itself is the function corresponding to the series. So if a series lies within the region of convergence, then the Z transform in that region will have all of its derivatives exist, and there'll be continuous functions of Z. All these nice properties exist when you lie in the region of convergence, and that's the really important thing about working in the Z domain. Once you're in the region of convergence, you have a lot of nice things that you can do with your modeling there. Now, the big negative is, just like in the Fourier domain, certain sequences like the sinc function, cosine, they weren't summable in the case of the Fourier transform, and do not result from evaluating the Z transform on the unit circle. And this is probably something that you remember from the S domain and Fourier transforms. I remember when I was in circuits a long, long time ago, I thought I could just, if I was in the S domain, I could just set S equal to j omega and look at that function, and I would have its Fourier transform. And then I realized it doesn't work, and I was really upset about that fact. It doesn't work. Why doesn't it work? Well, it's this point right here. Those are not the standard types of waveforms. So you just have to be very careful to not get carried away with this idea of sampling around the unit circle to get the Fourier transform. But how many of you already knew that from previous signals and systems stuff? Vaguely? Or were you ever disappointed in some math, in engineering math, that doesn't work the way you think it should work? I mean, it's just reality, though, right? Why do things have to be a certain way? Your notions don't necessarily align with reality. Okay, but we still are interested in those signals just the same. So we just have to be careful in how we deal with that. And those signals show up in our Z transform tables as well. The bottom line is, they're not going to be continuous, so they're not going to have regions of you don't have the region of convergence existing, maybe even on the unit circle, but yet those signals exist just fine. Most of the time, though, we're interested in Z domain functions that are rational. And this is the beautiful thing that you see in the S domain too. You have a ratio of polynomials in Z versus S, and then the region of convergence is well understood, and everything boils down to poles and zeros relating to where the numerator polynomial goes to 0, those would be the zeros, and where the denominator polynomial goes to 0, that would be the poles. So we just start thinking in terms of poles and zeros. So let's take an example. I have two basic examples. one with a right-sided exponential and one with a left-sided exponential. And these kind of set the stage for everything else that follows in the forward transforms. So a to the n u of n, we remember that as being our discrete time low-pass filter's impulse response. Remember y of n is equal to a times y of n plus x of n. I mean, a times y of n minus 1. It was the output of a first-order difference equation was the input plus the output one time sample earlier times a constant, a. So that's where this impulse response came from. This could just be an exponential sequence, though, that's moving to the right. It starts at some point on the integer axes and is non-zero from some point forward, but it's 0 before that point. So that's the right-sided sequence. So plug that into the Z-transform definition. Use the u of n to control the lower sum limit, and then bring parentheses around the arguments to factor out the n. And so we have a times e to the minus 1 and n. And now, because we're getting so used to identifying geometric series, we say immediately that's an infinite geometric series. It's going to be absolutely summable. In other words, have absolute sum less than infinity, provided that this ratio a times e to the minus 1 has magnitude less than 1. Is this burned in your brain good enough after a few weeks that you just think that way? So then you spin that around, and then you get, oh, okay, region of convergence, we're going to be guaranteed of absolute summability if the magnitude of z exceeds the magnitude of a. So then we can define the region of convergence formally in math notation as a point set of point z such that magnitude of z is greater than magnitude of a. I'm okay with just saying ROC is magnitude of a greater than magnitude, or magnitude of z greater than magnitude of a, but this would be the formal math notation of it. Question? So now what we have for our z transform, we go back and just evaluate this without the absolute value sign, just using our geometric series sum formula, and we get 1 over 1 minus the ratio, which is a z to the minus 1, or in positive powers of z, where we multiply by z top and bottom, z over z minus a. So this form right here is sort of a form that lets us draw a plot of the poles and the zeros and identify the region of convergence. This form over here with the negative powers of z is the way we generally operate with further mathematics, because we think in terms of negative powers of z, meaning one sample delays. We'll see that pretty soon here too. Z to the minus 1 corresponds to a delay of one sample, is what we'll have shortly. And dry humor that when I was in school, people would talk about going into the Z domain, and what is the Z domain in life? Sleeping, right? Because that's why cartoons generally show somebody, if they're sleeping, there's Z's coming out of their mouth or something. So you can use that interchangeably maybe, but you can't get your homework problems worked out if you're sleeping, unless you're thinking about a problem as you fall asleep and wake up with it, which I bet some of you have these phenomena where you're in the shower in the morning and the thing you went to bed wondering how to solve all of a sudden pops into your head when you wake up in the morning. That's pretty common for me. Or if I'm coming back from a walk, last week I was debugging code a lot, I just couldn't figure something out. I walked in the house and all of a sudden, bam, it hit me. That's why that's not working, and I went back and fixed it and it worked. Why can't I think of things at the moment? Sometimes the pressure builds up too much and your brain can't think. Okay, so plotting the in the Z domain, then this is the Z plane showing what the Z transform looks like. It has a 0 at 0, and that's because of the numerator polynomial is just simply Z, and then it has in the denominator a Z minus A, so that says Z equaling A is the pole. And the fact that it's located here on the real axis is assuming A is real in this case. Let's see. But in reality, A can be any complex number, so it could be anything, and then it would be some other place on that circle of radius magnitude of A. So picture might not be the most accurate, but it's representing the idea that now we have a region of convergence, which is the exterior of a circle of radius A, or magnitude of A, and that pole is setting that region of convergence. See, the idea is the sequence is moving to the right, and it's going to be the exterior of a circle of radius A, and we're going to have eventually that it will, if we have a collection of poles, it will be the largest pole radius that will set the region of convergence for right-sided sequences, a linear combination of them, let's say. We're going to take the break and just as soon as I look at this one. So now let's take and turn that sequence around, let it be an exponential that's running in the opposite direction. So it's, for convenience in the transform pairs, we're going to define it to be minus a to the n u of minus n minus 1. Now that looks complicated. It's just a sequence, though, that is starting at n is equal to minus 1. And running backwards. So plug that sequence into our Z transform definition. The upper limit gets set by the u of minus n minus 1. So we sum from minus infinity up to minus 1, and then we have as our argument a to the n times z to the minus n. And you can sum that using a change of variables. So I take the lazy way out. I'd simply say this sum can go, I can just change the polarity of the indices, and I'm going to change the polarity to be 1 to infinity, and then all my n's here have to be replaced by a sign change, so a to the minus n and z to the plus n. And then I say this is getting very close to the standard geometric infinite series starting at 0, but I have a minus sign out in front, and I have to deal with starting at 1, so I have to be careful. I'm going to start my sum at 0, but then I'm going to remove the term that corresponds to n is equal to 0, which in this case, because of the minus sign, is just adding a 1. So do you see that what I'm doing there is I'm just rearranging things, and I'm taking into account that 1 is to annihilate the n is equal to 0 term. Does that look okay? And then I can sum that series just like before, except now the region of convergence is going to be the magnitude of z less than the magnitude of a. And when I put that back together, z transform of this guy, this is the only sequence that really doesn't do anything exciting. I z transform 1, in other words, a sequence that only has one point in it where n is equal to 0, and I get 1. And the region of convergence is everywhere, but there's nothing going on there, so it's not really very exciting. But it is a special property, though, for the constant. So I get 1, and then I subtract the z transform after I look at the geometric series sum here, and then I put it over a common denominator, and lo and behold, this matches. That's the same form. But this is different. So what's distinguishing in the Z domain the two signals, one that's right-sided, the other one that was left-sided, is the region of convergence. So the ROC now is the interior of a circle of radius A. So we have interior and exterior, and later on I'll be talking about some of the theorems, and one of the theorems is going to say what happens if you turn this inside out, what would it be? If I turn this region of convergence inside out, it would be flipping it from being the interior of a circle to the exterior of a circle of radius 1 over A is what would happen. And I have a bizarre analogy to that. I call it taking my socks and turning them inside out. I mean, sort of a visual of what goes on when you do that. And speaking of that, I'm wearing these compression socks right now because that's putting pressure on where I had had the incision and the surgery on my right leg. So I'm thinking about that, how painful they are. I'm not fond of wearing these things actually, but supposedly I'm going to heal faster if I keep wearing them. Wearing them is not as much trouble as getting them on is and getting them off. If any of you ever have to do it, some people have to wear them every day of their life because it's part of their medical circulation issues. What's that?
I have a brother-in-law that wears them every day.
Yeah.
They're knee-high.
Yeah, mine are just below my knee right now. I slept in them actually. Why did I sleep in them? It's because the wrapping around my calf, which is where the excision was done, the bandages were sticking on the blankets, and felt like I was going to rip this wrap off. So the compression socks are really smooth, and I'm getting pain standing right now because I know there's stitches in there. There's stitches inside and outside both, and I'm just feeling this little bit of pulling action going on if I stand up too straight on my calf. So a big push right here, and this is something I'll be looking for when you do your homework and also when you do an exam problem, is you're going to have to give the region of convergence. So I want that to be with the transform, because we can see right now that it makes the Z transform, the Z domain, unique when you go back to the time domain if you know what the region of convergence is. Because if it's the exterior, it's going to go back to the right-sided sequence. If it's the interior, it's going to go back to the left-sided sequence. Okay? We'll come back to this after the break in about 15 minutes. So I'm going to try to make sure I pause the recording. Okay, we've got more stuff to do, obviously, and I like getting through this chapter. The next chapter is going to be pretty crazy with the sampling theory stuff, which is very, very practical and very hands-on oriented. This is just a part of the tool set, and this is a very important part of the tool set that you use the entire rest of the semester. So we're headed towards inverse Z transform, but we're doing a few more forward transforms, then we'll kind of back off and summarize. I'm going to drill you on regions of convergence. I've got an example on that coming up here too, where I'm going to try to have you look at something and tell me. It's like a matching game. What does it mean if this is true, and so on and so forth, because it's like being a detective. That's what engineers have to do. Sometimes we have to be a detective and look at a situation and try to figure out what's really going on. So from what we've done so far, which isn't very much, we can put together a sum of two sequences and learn a little bit more about how that impacts the Z transform. So here we have just two right-sided sequences, and taking the Z transform here is just simply going to be relying upon this transform pair. And I think what I need to do is just go back and refresh my memory. I'm looking at, going to look at the exam tables here. So this is what you're going to be looking at using frequently as you're getting things in your brain. So I guess I can draw on this because I'm in this guy, right? I started off using this as my editing tool, but I could highlight it, but that's the one we're looking at right now. And the one just below it is the transform pair we developed right after this one. And then we'll move into other variations on it, but these are the core transform pairs that we'll be using. This one right up here with the z to the minus m, if you set that to just be z to the minus 1, then that says it's just a delta of n minus 1 is what that is. So that idea shows up a lot in the block diagrams and such. The single sample delay is what that means in a system sense. So keep thinking about this, and you're going to be looking at how you use this table. This one and the one right beneath it are probably the most popular ones that we use, though. These two are like the duals of each other. And if you're not looking carefully, you just need to pay attention to one is the exterior, one is the interior. And that's pretty much what these do all the way down the page. They're flipping back and forth to some extent. So back over to this. Z-transform operator is linear, just like the Fourier transform is. So if we have a pair of sequences, we can transform them at the same time. So we're going to use this linearity property. And what we have to be careful about now when we bring in two sequences is what is the region of convergence of the total sequence. And so we have to go back to set theory in mathematics and say that this will have a region of convergence, this will have a region of convergence. What is the region of convergence going to be? It's going to be the intersection of the regions of convergence. So the only thing that's going to differ on this, which I'll get to in some examples later, if there is something called a pole zero cancellation, then the region of convergence can get bigger again. In other words, that the region of convergence is being constrained by either a right-sided or left-sided sequence, but if when you form this sum here, you get a root in the numerator that cancels one of the poles in the denominator, then it makes it bigger again because of a pole zero cancellation. So we put this example together, and this is how it starts then. Just forward transform, it's very trivial to do, but then you have to think of what are the regions of convergence for each of these. You've got two down here, that and that. So which one forms the intersection? It would be the max of 1/2 and 1/3, so that will be 1/2. And then if you put this over a common denominator and, yeah. No, it's the magnitude. Right? That's the region of convergence, it's the magnitude, so. Don't skip this last step. I realize you say it's only algebra, but do it because you need to do it so you can see what's going on, because you're missing something if you don't do it. When you put it over a common denominator, now you can see what you have in the numerator is another polynomial, and you can see that you have two zeros in the numerator. And in this case, there's no cancellation happening, but if there was a cancellation, you won't be able to see it unless you put it over a common denominator. So not only that, I'm going to insist that you do that, so I'll deduct a point or so if you don't do that, especially if it factors into the ROC. But here, it doesn't. You can see the two poles are intact, one at minus 1/3, one at 1/2, and then there's a 0 at 0 and a 0 at 1/12. The zeros don't enter into the region of convergence, but the poles do, and it's the larger one that sets the region of convergence. And if you think about this, if we're going to allow convergence for anything greater than 1/2 in the z-plane, then that other pole at minus 1/3 we never get close to it. If we get close to it, then we have a singularity there. We have a 1/0, right? So that if you just look at this picture, you say that's why it has to be that way. This might help you understand how the poles factor into the region of convergence. We're going to be outside of that by being at 1/2. Greater than 1/2, we'll never have a 1/infinity or 1/0 situation going on. We could take the same example and make one of those sequences run from the left side, and then we'd have the inverse Z transform, or the Z transform, would be the same form, 1/1 plus 1/3 Z to the minus 1, but now the region of convergence will, second one, I got this. Now we're the interior. So if I was to redraw that picture, now we have the annular region where we have the same x of z, but the region of convergence now is the annular region, because that is the intersection of the two regions of convergence. And if you're thinking ahead, which you should be, I think, if the sequences were going in the opposite directions each, then there would be no intersection. So then the Z transform doesn't exist. And you say, what do you mean by that? Well, it doesn't exist because there's no sequence that would correspond to that Z transform being absolutely summable. Don't worry about that, though. I mean, it's just part of the math. That's what the math brings with it.
Which, conceptually thinking about this, if the Z transform is how we take a signal and break it down to something that we can accurately see and measure. Just breaking it down to small parts, and it's a way that we can analyze the signal, right? So,
well, working in the Z domain is yes, but it's an abstraction now. Remember, I said this about the Fourier domain too. You go to it to see something, but we live in the time domain. We don't live in the Z domain or the Fourier domain. It's just a domain we switch to in order to do some modeling or analysis, but it's not where we actually operate. We operate in the time domain.
So if a Z transform doesn't exist, does that tell me that, okay, this signal is something that I can't analyze by looking at a small window of it? What does that mean?
It just would not be practical to have such a thing. You'd be having something that would not be absolutely summable. It would go off unbounded. So it wouldn't exist as a physical entity because it would contain like infinite energy or something like that.
Okay.
I think I could probably put that together as an example and try to prove it to you. I generally don't go off and try to think about it because it's not something that we're going to run into in a practical setting. But the math, the math always seems to have more capability than what we want to get out of it most of the time with our modeling. And we know that we can pretty much go off the rails with things if we take it to the extremes. And that's what's happening here. The annular region is really not going to come up that often in a practical setting because generally we're doing real-time signal processing and we won't have left-sided sequences. But if you were collecting data and you wanted to do something with it, you might want to use some non-causal signal processing. Like the best example I think about is filter, which means you filter a signal that's been captured twice, once going forwards and then you flip it over and filter it again as if it's running backwards. And that's a good modeling tool, but it doesn't mean that you actually can do that in real time. You have to do that offline. And we do things like that, I guess. In HDTV, we have an image, and they're doing things to try to transmit that image with all that fidelity in the modulation theory. They can do things with images because you can filter in the opposite direction. I mean, an image is an image. It's not like it has a start here, start there. It can be scanned all different directions. So I know they play some games there. I don't do that, so I don't think that way, but I think they do in the algorithms that are used, say, in HDTV or image processing in general. We're in the one-dimensional case. So same pole zero plot, region of convergence is different. If we have a finite length sequence, we always have a region of convergence that is able to go all the way out to infinity, or go all the way to 0. So it'll depend upon where does N1 and N2 sit. So if N1 and N2 are both greater than 0, then we'll have negative powers of z. So we look at this x of z, what's going to make it be unbounded is only if we, for values of z, it's only going to be at 0, because we'll have 1 over z everywhere in our expression up here, so we won't be able to let the region of convergence go to 0. So we'll have to exclude 0. So that's this case right here. If x of z only includes negative powers of z, then the region of convergence has to be greater than, magnitude of z has to be greater than 0. That makes sense, doesn't it? Negative powers of z means we have a 1 over z, and if z tries to go to 0, any one of those terms is going to go into infinity. On the other hand, if the sequence exists, I guess I've got the mixture case here, well, only positive powers of z, then that means the sequence is on the negative time axis, and we only have positive powers of z in the z transform, and then region of convergence has to be less than infinity. So those are those two cases. And if we have both positive and negative powers, so our finite duration sequence is sitting across the boundary of n is equal to 0, then the region of convergence has to include both infinity and exclude both infinity and 0. And that's a fancy bunch of statements there just to simply say that if I look at this, I know from seeing what positive and negative powers of z mean, what I have to exclude. The important thing, though, is when we're doing inverse z transforms, we're trying to discern things, and these little properties just come in handy. If you know you can't go out to infinity, what is that going to tell you about a sequence? It must have some terms for n less than 0. And think about causality. What did we have with the impulse response? It had to be 0 for n less than 0. So how does just trying to think about that, what would that mean? If the impulse, if the h of z for our system says the region of convergence has to be less than infinity, that says that we can't have any positive powers we must have positive powers of z in our z transform, which means we must have some negative terms, negative n terms in the time domain, which means we're not causal entirely, right? I'm just giving that as an example, but what I'm saying is there's implications, and those implications can come about from knowing this information. So some of these homework problems will work with those understandings where you have to read carefully between the lines to say, I know this is true, so this must be true, or this must not be true. So I guess causality in a sequence, like as in the impulse response being 0 for n less than 0, says that we have to be able to go out to infinity with the region of convergence if it's a causal system. And we'll bump into that later. So rectangular window, let's do this one. And then I think, we go into properties, and when I get down with these properties, I'm going to take this and talk about what are the 4 possible choices for the region of convergence. So this is kind of like a quiz time in class where I'm going to ask you some questions. But we're going to first do this one. This shows up pretty regularly in signal processing, a finite window, whether it be a rectangle or an exponential finite window, a to the n over points from 0 to n minus 1. How do we get this Z transform? Well, we get it easily from the finite geometric series, right? So we just say this is a finite duration sequence. We know that its region of convergence is potentially 0 out to infinity. It might exclude 0. We might exclude infinity. But we know that it's of this form, so let's try to dive into it and see what's going on. We take the finite geometric series formula and get this down here, and then I do some factoring on this to get it in positive powers of Z so I can identify poles and zeros. And this seems, this routine of having to go from negative to positive and then do analysis in negative seems awkward, but I have an easier time identifying poles and zeros if I think in terms of positive powers. That's the reason why I do it. If you're okay and you can get good at it, do it, but you just have to be more careful. We want to work with negative powers because that's the way our tables are going to work always. We're going to be using the negative powers, and we'll do that, and that'll be the way the partial fraction expansion is going to be set up to work. So at any rate, we're now in positive powers of Z, and now we can identify where the poles and the zeros occur, but we have to be careful. This is actually totally solvable, and that's what the last bullet talks about, which I'm prepared to talk about more fully. We have in the denominator here, we have an nth order polynomial, so we want to know what the roots are associated with that nth order polynomial. We have a first order polynomial here. What are the roots of that polynomial? Well, that has a single root, and that Z minus A just has a root at A, right? Has a pole at A. And right next to it over here, we have this E to the n minus 1. What does that correspond to? A bunch of poles at Z is equal to 0. There's going to be n minus 1 of them, right? Because E to the n minus 1 says that there's n minus 1 z's all multiplied together in the denominator, so we have a pile up of poles down there. What's going on in the numerator is we'd say it's an nth order polynomial, there must be n zeros, right? But where are those zeros? So, and I also stated that the region of convergence has to be this, and that's just true because all the powers of Z that are going to be in the Z transform are negative. And that we know from the previous page was meaning that 0 is excluded from the region of convergence, but we can go all the way out to infinity. But now this bullet right here is a sticking point, and I actually prepared for this a little bit this morning. I said I'm going to want to talk through this. I'm going to want to remind you of what is going on here. And the problem is this. Maybe this is a good way to try this. It's not working. It's supposed to be highlighting, I think, but it's not working. At any rate, I'll just do this. This is something that you learn in Calculus 2, and I don't know exactly where because I don't remember where I learned it, but n roots of unity, do you remember that? Ever from somewhere? I'll just leave it like that. What values of z when raised to the nth power will equal 1? Remember this from somewhere? Maybe in the S domain, maybe in calculus, what I'm saying. What are the n? This is called n roots of unity. Or it should be capital N, I guess. Well, that's one of the roots. So this is what's going on here. If you take that z to the k and raise it to powers of n, so a e to the j 2 pi k and raise that to the nth power, what happens? You get a to the n and k is thrown in there. It doesn't matter what k happens to be equal. No matter what k is equal, we have e to the j 2 pi, and that's always going to put us right back at 1 on the unit circle. So we have, these are the roots then. The roots can be located at these locations. The roots are spaced around on the unit circle at radius a at all the angles going around the unit circle. And that's over here. In this picture right here, they're spaced at angle 2 pi over n, capital N, and there is a root nominally right in here, but in this system, there's also a zero that's sitting right there because the numerator over here, or the denominator, that has a root at z at, oh, wait a minute, never mind, I'm getting this, yeah. That is a root at z is equal to a, and then there's also a root at z is equal to a in the denominator. So those two annihilate each other, pole zero cancellation. So that's the characteristic of this rectangular window, and whether a is 0 or 1, it doesn't matter. I mean, whether a is 1 or greater than 1 or less than 1, this system is always stable. So this, I want to talk about this really briefly because it's something that's kind of nice to model. Let's see. Guess I'm over here. I have to go back to the Jupyter notebook. So here I have my Chapter 3 Jupyter Notebook, which I think what's on the website right now might have this line with pandas in there, which maybe I'll talk about it sometime. Does anybody know what pandas is for Python? It's a library for sure, but it's one that's used in data science and it's for working with tables of data and manipulating things around. I just used it because it can put a table of, it can display a nice tabular form of some arrays, and I occasionally had used it. If you wanted to put it on your system, you would just go to conda install pandas, and it will put it on your system. It'll pull it down and put it on there. Believe it or not, pandas was developed by one of the coding guys at, I think, the New York Times, who used Python, and he developed it as a tool, and I think it was because he was managing subscriptions. I don't know this. I mean, I've been to the Python conference enough, and he was there one year, and they talked about the beginning of that package. And how is it connected with Python? Well, analytics and data science, but why would a newspaper company care about that? They were studying, I think he was interested in subscriptions and where subscribers live and habits and everything, because to me, reading a paper newspaper is just something I don't do anymore, and I know newspapers have been struggling with how to stay in business. Has anybody ever thought about that? How many of you read a paper newspaper regularly? What's that?
That's the thing of the past now.
Yeah, right. Yeah, exactly. Exactly. So what can you do in Python, though, with this? I'll just start this over again. These are some tools that we have available, but I'm going to restart this notebook just to make sure we're clean. Okay, so we already played with this. There's not really a whole lot to use Python for in this chapter, but I do have some useful things we'll get to. You can check pretty much all of the inverse Z-transform problems in Python. And we have a tool in the SIGSYS module called zplane, which is similar to what you have in MATLAB, but it's something that I wrote for Python. And it produces the pole zero plot of a ratio of polynomials. So Z plane, if I do help on it, you're putting in the numerator coefficients first and the denominator coefficients second, very much like what you do in FreakZ and L-filter and so on. And then I have some other attributes in here that can be used. Why didn't anybody ever write this? I don't know, but it was one of the things I had to have because I thrive on pole zero plots, and I want you to use that pole zero plot as a tool to see what's going on. So here I just put in 1, 2, 3, 4, and it gave me that. Let's put in that. And it does that. Now, we'll come back to this in Chapter 5 when we're talking about minimum phase systems, but what I just did is reverse the order of the polynomial coefficients, and that made all of the coefficients, all of the zeros in this case, flip to reciprocal locations. So they were outside the unit circle, and now they're at the reciprocal locations inside the unit circle. Well, not a topic to drill into right now, but we'll study that later. It's an interesting property. It leads to something called an all-pass discussion of an all-pass filter, which is part of filter design for phase equalization, and just other things. I mean, pole and zero plots have a lot of interesting properties that you can observe and just get a feel for systems. So now the rectangular window, I'm just going to take, set A equal to 1 here. And first off, there's a plot of the sequence, and then a subplot. There's a plot of the pole zero plot. And you'd look at this and you say, is this right? I had 10 points in my sequence. The degree of my polynomial is going to be 1 less than the number of coefficients. Is that right? A quadratic has a constant, a first degree term and a second degree term. So how many roots are in the second degree polynomial? 2, right? So we have 9 roots here. And in the case of the rectangular window, the number of zeros in the denominator, remember, was z to the m minus 1. So if m is 10, we have 9 poles at z is equal to 0. That's what that represents right there. And then here's all of the zeros spread around on the unit circle. And there was a pole and a 0 sitting over here, but remember, they were canceled out in the math. They were annihilated. And this actually means that if this was a system, and if we were to do the frequency response of that guy, which is done right here, we have our alias sinc function frequency response that we saw before. The rectangle gives rise to that. If I was to go up here and make A equal 0.9, it doesn't really change things that much, but it changes it a little bit. Now the sequence is exponentially decaying, and now in the pole 0 plane, the poles are still at z is equal to 0, but now the zeros are sitting just inside the unit circle. And if I was to do the frequency response, it will change the shape ever so slightly to look like that. And you're probably thinking, okay, what else can we do? What happens if we set this equal to 1.1? It's exponentially increasing, but it's finite, so it's still going to be stable. Now the poles or zeros are outside the unit circle. The poles are still at 0. If we go down here and do this, it doesn't change. I mean, this is the magnitude response. The phase is going to be different, but it's still stable in everything. The gain is a little bit different too, but that's about all I have to say about that. We're going to be moving into inverse transforms here very soon, but more other examples back over in the notes. Any questions, or do you have on this? Does this bother you maybe? I'll actually have a tool that we'll be able to look at this with later. Can I even find those tools on here?
I just have a question on that. The way you wrote the code for the frequency response factor.
Right.
Do you prefer us to use the freq z on that?
Right in here.
Yeah. Do you prefer that? Because what I've been doing, I was just doing the absolute value of whatever I had.
You didn't use freq z though. You just did it in all Python code.
Yeah.
I prefer you to use this because it's faster. If you want to write it out term by term, you can certainly do that. I mean, that's legit for sure. I just like leveraging the power of the tools if at all possible, as long as you understand what it's allowing you to do. I was going to try to find in my folder. I don't remember where it's at, so I'm just going to start here.
I mean, using that, how would you plot the phase?
Okay, you would use angle. I'm going to jump and try to find that here right now, if I can. Under projects, I'm trying to remember where did I have this saved? There it is. This was something that I wrote a long time ago in a language called Zojo, and I can't have this on the website right now because it takes up too much space to deliver the library that goes with it, but I can certainly get it to you in Slack. But this allows me to drag things around, so I can move a pole and zero around, and here I can plot magnitude and phase if I want to. So we were just talking about having a zero inside versus moving it outside. We just get a different shape to the phase response, whereas the magnitude response would be roughly the same. And I could type more coefficients in up here if I wanted to. I think if I remember right, I could go 1. I think. I'm going to probably have to remember how to make this do that. I don't play with this too often, but I will be demoing it in chapter 5. I think this one, pole zero geometry. Yeah, here's the moving average filter. Here's where there's a certain number of zeros. I guess I don't have a high order one, but you can see by sweeping around the j omega axis we get, the e to the j omega. This will be part of chapter 5, but we're seeing we're getting the frequency response in the nulls of the frequency response occur at these particular angles. This will make a whole lot more sense later, but suppose we wanted to do an elliptic filter. There's an elliptic filter right there, and if I put it in decibels, it has that sort of response. And right now it's just intriguing, but those are the coefficients that form that filter, and the poles and zeros are over here, magnitude and phase form. See what lies ahead, but I'm not making you, I don't want you to understand it, but this is practical, being able to design a filter and then understanding how my main theme of even doing this is that you see how the pole zero plot is so important. It gives you a tie back to visualize things from a geometry standpoint. It's kind of why I wrote this stuff. I wrote it a long time ago. It was my first delving into object-oriented programming in this language and writing graphics utilities to do the graphics from scratch, and being able to move mouse around and drag stuff around. I learned a whole bunch of stuff I never really thought I'd learn, but it was fun because I'm that type of person that tinkers with stuff. So I get into writing code at that point. Okay, so we'll come back to this and we'll see these sorts of things happen, and you've got some things in the homework problems that deal with this too. In particular, you've got a triangular shaped impulse response, which you study in the form of the convolution of two rectangles, because remember that convolve two rectangles and you get a triangle. And we want to see what that does in the z domain. So it will be related to this. And since I'm already talking about that, let me just jump over and just let you see how you could go tinker with that if you wanted to. So suppose you were interested in that, and I might actually have it in here. I probably don't. So I would just go up here So suppose we wanted to see what would happen if we had a triangle. We could go 1, 2, 3, 4, 3, 2, 1. So that's a triangle shape. It's going to climb up and then climb back down again. And what it's going to be, it's a sixth-order system, and you can see that in this case the roots are repeated, and it's because of the convolution theorem, actually. We're taking a rectangle and cascading it with another impulse response that's a rectangle, and in the z-domain that will be the product of those z-transforms, which will be repeated roots then. If we have a root at one location, because it's cascaded with the same system, it will get repeated, and that's why the 2's are on there. And you'll be exploring that in one of the homework problems, or you do explore that. Is that interesting, or is it too much to absorb? There's a lot to absorb here, but it is interesting things. And you can explore things like this, though, in Python if you want to go play with it very, very easily. And I didn't say, but you will have some systems where you might have coefficients over here. So you might have 1, minus 0.8, and that would be our simple exponential term. So if that was to pop up in here, there it is. Now one of those poles that was at 0 is gone, but now we have a pole at 0.8 that came popping in there in the math of the whole thing, just because of that. And of course, if I went back to this just being 1, then we started with this at the beginning. Not very exciting, though, but so you can check things out and you can get this picture. The only thing this can't show you is the region of convergence. I dreamt about ways of trying to make that happen, but I've never really been interested in going back there again. It's something that could be done, though, I'm sure. So the next thing is properties of the region of convergence. And these are things that you're going to gradually grab a hold of, and then you're going to leverage this to understand how to go both forward and backwards in your z-transform. So it's always an annular region, and that's just property 1. We talked about that. We get convergence of the Fourier transform, absolutely if and only if the ROC includes the unit circle. We talked about that one. The region of convergence cannot contain any poles. We've sort of implied that already. If there's a pole in the region of convergence, it's like you made a mistake. Because if you can go to the location of the pole thinking that you're going to get an absolute sum, this is our normal problem. It goes quiet in here. Back on again. And I think about this problem this morning. It's like these guys still haven't gotten back to me with my ticket, and how Dr. Trimboli says, what kind of an organization do we have here if maintenance people can't provide better quality of service? What do you guys think? Because I will bring this to them. It's like it's been 2 weeks now since I filed this ticket, and they can't swap out and put a different projector in there to solve it. They want to fix it by ignoring it, I think. But at any rate, I don't want to go outside tangenting that. You can write me on Slack, though, because I'm going to tell him right after class here that it still is wiping me out. At any rate, those of you watching the video, it's intact. So, lost my train of thought, though, a little bit. You just know if there's a pole inside the region of convergence, you'd want to walk right over by that pole and say, can I evaluate z here? And I'm going to have a 1 over 0 somewhere. You can't, that's not good, right? It's going to be unbounded. Property 4 is a finite, if you have a finite duration sequence, it's the entire z-plane except possibly 0 or infinity. We've addressed that already. And the entire z-plane only exists if it's a constant signal. And that's very uninteresting, like a gain in an amplifier. if it was a signal processing block. And now we have property 6 and property 7, which are kind of duals of each other, and these have a lot of parts to them, but these are things that you're going to eventually get a hold of, and we're going to look at this example before we leave today. If x of n is right-sided, and right-sided says that x of n is 0 up until n is equal to n1, no matter whether n1 is less than 0 or greater than, but then the sequence is non-zero as you march forward. That's the right-sided sequence. The left-sided is the opposite of that. It's 0 beyond n2, let's say, and then it's non-zero for less than that. But the right-sided sequence says that the region of convergence is always going to be the exterior of a circle, and that circle, let's see, get the right tool here. And that circle corresponds to the magnitude of the largest pole in the x of z function itself. So it's always going to go with the maximum. The region of convergence sets that because when you go outside of a circle that's the maximum pole, you know that any other poles are going to be inside and they can't be in your region of convergence. So it's the outer maximum pole that sets the outer radius. Does that make sense? We can go out from there and we're safe. I'm kind of skimming over some of the other details. I guess the last bullet there really summarizes the whole thing. In the left-sided sequence, it's the same thing. It just says it's the opposite, though. It's the interior of a circle. So and it's the smallest pole radius. So if you're going to be inside a circle, as long as it's the smallest pole radius, other poles may sit around that, but as you go in, you'll be safe. You won't have any pole that you can bump into. And if you have a two-sided sequence, that just means you've got a combination of left and right-sided terms in your underlying sequence. The ones that are right-sided will set the outer radius, and the ones that are left-sided will set the inner radius. So
only the highest value for the outermost and the lowest value for the innermost?
Correct, absolutely correct. So now we're going to test our knowledge and see what makes sense. So we have a pole zero pattern that happens to have, and the answers are down below this. I'm just going to stay here. So A, B, and C, and just suppose C is outside the unit circle and A and B are inside. What are the 4 possible choices for the region of convergence, and then what are going to be the corresponding sequence types that come from each of those poles? So based on what we've just talked about, you should be gravitating towards an ROC that's magnitude is greater than C, right? Because that would be the exterior. So one could be exterior radius. If that was the case, all A, B, and C would all be right-sided sequences, right? They'd be all moving off to the right for non-zero values, and it's just the one with the largest pole radius that's at the ROC.
I thought, the strengths in my head, I guess, with those properties we were reviewing earlier, if they were inside the circle, they were left-sided, but because they're on the right of 0, they're all right-sided because they're positive integers?
Well, it's not because A and B and C are positive or negative. It just has to do with the region of convergence being the exterior of the largest pole radius. And of course, the ROC can't contain any poles, so it's a valid ROC, but all 3 of those terms are right-sided. Let me see if I can get this to delete easily. There we go. Okay, so what's another choice that's a possibility?
Everything inside of A, radius A.
Yeah, right. So those would all be left-sided sequences, because it's the interior of the smallest pole radius for the left-sided sequences. Then we have the mixed case, then there's mixed cases. So how many mixed cases exist? If we have the interior, the smallest, the exterior, the largest, then we have two other annular regions that are between A and B and between B and C. So if that's the case, if we're between B and C, then what's the direction of A, B, and C sequences then?
Assuming A and B are right-sided and C is left-sided?
Right. Does everybody follow that? Because A and B are, we have an exterior that departs from B, so A must be also a right sequence because it's inside of it, so it's going in the same direction. And then the C must be left-sided because it's pulling in. It's the smallest pole radius of the left-sided sequences. So these pictures are just the four combinations. Figuring out which direction the sequences go has to follow from the interpretation of either the largest pole radius or the smallest pole radius. Again, most of the cases are causal, and we have right-sided sequences in most practical scenarios, but you could be doing offline processing, in which case then you might have this stuff happening. How often do I bump into this in working with real-time systems? Never. But, possibilities are possibilities, and there's just interesting phenomena. I mean, it's part of what I think has to still go on in teaching this class. That's my feeling, at least. Okay, we have about 10 minutes left. This is another important topic. This is actually, you're having homework problems on this too. Stability, causality, and the region of convergence. So the region of convergence is also a key to us understanding all of these things. And this is very powerful, and it's very cool the way it works out. And I've given you enough information so far, and let's just pull it into practice, because I think after this, so this is a case in point, but we could do more cases in point. So here we have a pole at 1/2 and one at -2. So there's 3 valid ROCs for this. There's the exterior, the largest pole radius, interior, the smallest pole radius, and then there's the annulus between the largest and the smallest. So your mind should be whirling. What are those things talking about then? If it's the exterior of the two, then both the sequences are right-sided, and we know none of them are left-sided. But the question up above is what is stable and what's causal, just from looking at this. So absolute summability assumes that we have stability. If this was the impulse response, this is the theorem from chapter 2. So stability requires, as I've already said, but I'm saying more formally now, I guess, the ROC must include the unit circle. okay? So only the annular region solution is going to be stable because that's the only one of these three possibilities that will
Just because it's contained within two poles, is that why it's stable?
it doesn't well, it's stable because the ROC contains the unit circle, so it's this.
Oh,
Okay, it's simpler than what you were thinking.
okay.
It just has to contain the unit circle. Now there's a dilemma here though. If we have the annular region, one of the sequences is going to the left and one of them is going to the right. So the right-sided sequence is going to be fine for causality, but the left-sided sequence makes it impossible to be causal. So under this condition, the system is not causal since we have left and right-sided terms. And you say, that's too bad. How can I deal with that? Well, that's sort of another matter, but it's the fact of the matter is we can be stable, but we aren't necessarily causal.
Is that a constant truth just throughout all of this as a principle? If I have a right and left-handed sided term, it can't be causal?
Right.
Okay.
Because if it's left-sided, it's always pushing to the left, and it's always going to have to exist on the negative axes, and that violates causality, right, for an impulse response. But we'll learn eventually that what we'll be able to do, we can put this at the conjugate reciprocal location, which will be somewhere right in, let's see, I guess it's going to be in here more, but we can move it inside the unit circle, in which it'll be at 1/2. So then we can make the system stable and causal, but we'll get a different frequency response. And the big example that I can give for that is if we're looking at this as an impulse response, we could think that if we're in a multipath radio communications channel, I'm just giving this a very practical example, it could be an acoustical phenomena too, where you're trying to equalize reverberations and flatness of frequency response, like a sound engineer would have to do for a recording studio. What will happen is that it'll have to do with the arrival of wavefronts at us, like in a radio communications channel. When we have multipath, we're getting a direct path, which is going to be the shortest path, and then we might be getting another path that bounces off a wall, bounces off another wall, and comes to us eventually. Does that make sense, that we can have that ray trace? And the ray that bounces off the wall is going to take longer to get to us than the one that's directly. Now, what makes this become non-causal for equalization purposes is if the direct path is weaker than the path that has to take multiple reflections. And that's possible in mathematically speaking and in practice speaking. So it's not that the path is non-causal. What's non-causal, the path is an FIR system, so there's no denominator terms. It's all numerator stuff. But we'll have positive powers of Z in that Z transform, and then if we try to invert that channel by putting those zeros into the denominator to make an equalizer for the channel, then we'll be non-causal. That's where we have the problem. This example has poles in it though, so the case the radio channel case is the zeros case, which can occur in a audio processing sense too. I'm just giving you a little tidbit of something that's going to show up later. It's like, why does this stuff matter? Well, there are practical situations, right? And if you're like most students, you want to know what's practical about this and how I can use it somewhere or another. And equalization is an important thing in signal processing. How can you equalize the channel? And you'll be dealing with that eventually. we'll see that in Chapter 5 in particular. So the second bullet here says if the system is causal, then the system must be the ROC, that's the exterior, so it's this system here, because now both sequences are going to be right-sided and can be designed to set at n greater than or equal to 0. But now it's no longer going to be stable because we're going to have a minus 2 to the n u of n term from that pole that's outside the unit circle. Right? It's just going to be blowing up, and we can't build that system. So the blue line there of showing putting it inside is the only option we'd have to implement it, but then we'll have a different phase response. We can have the same amplitude response out of the system if that's what we were choosing to do for our system. I don't know, is that a showstopper? Does that make you feel really bad, like none of this stuff can be useful? We just have to work around it. The math puts us, can put us in a situation, and it can be driven by a scenario. So you'll have a homework problem where you have to answer these types of questions, and you'll be able to say it's not stable. It's stable under this condition, but not causal. It's causal under this condition, but not stable. That can happen. So we're actually on the verge of going to the inverse transform. There's these tables, but then we're confronted with the inverse transform. I'm just going to use the last couple of minutes. We have this contour integration, which is how we would do the inverse Z transform. And this is definitely a topic from complex variable theory. And it's called Cauchy's residue formula. Cauchy is a mathematician that shows up a lot in complex variable theory. Have you ever heard that name before, Cauchy? There's Cauchy sequences, and his name is on a number of different things. But we're mostly going to be focusing on partial fraction expansion, and that's, we'll be using the table and then the partial fraction expansion method. We are out of time, though. I was going to ask you, was there any homework problem that's bugging you right now? I want you to start looking at them. I will put hints out again like I have in the past. I could have gone down that path, but instead I just pushed harder to get to this stopping point. So we'll be starting at partial fraction expansion, which is a very nice, friendly technique. And once you get into partial fraction expansion, we have these expansion techniques that you've seen before, and then when we want to check our work that we've done it properly, we have, I'm rolling down to the Python section in here. We have this function called residue Z. So example 315 takes you through the use of residue Z. And what it provides in the homework and the examples here in this section of the notes work through the examples, how you can do an analytical solution, which you have to do, but you can check your work in Python and just know that you've done it correctly. And there's a couple of homework problems that are a little bit stickier than others. They're going to be higher degree polynomials where you're going to be a little bit frustrated by the math, but you're going to be able to just push your way through it. And the partial fraction expansion, getting the coefficients, what do you remember is hardest to do in partial fraction expansion by hand? Simple poles, and what about repeated poles? What are your memories of that when you have a pole repeated twice or even 3 times? It's a lot trickier to get the coefficients. So I'll discuss some alternative methods you can use, because even when you go to a pole that's repeated once, it gets really messy in a hurry. It goes ballistic in a hurry, so you end up using two equations and two unknowns. You might remember that technique from circuit theory, where you had to solve for coefficients not using the straightforward method. You have to go kind of around the backside. I'm going to sign us off, as in stop the video.